Lilit, she was working in a root team, and particularly in IRIS-HEP group. I was her supervisor, and also was Enrico Giro. We were both supervising Lilit, and her topic was basically to improve the root benchmarking, performance benchmarking infrastructure. So, Lilit, your turn.
Hello, everyone. I'm Lilit from Armenia, and I'm a bachelor student in the American University of Armenia, and I study computer science. For 8 weeks, I worked in Root, and my supervisors, Oksana and Enrico, who were great mentors for me, mentors throughout the process. Should I start with the slides?
Yeah, so I'm going to the slide number 2.
Okay. So I will talk about Root Bench. What is Root Bench and why do we need it in Root? New benchmarks that were extended in rootbench.git. Flame graphs, the new feature in Root Bench. Improvements in RB support library and future items. Okay, next slide, please. So what is root bench? As the field of high energy physics must deal with the large CPU and I/O costs of processing and analyzing billions of events, software performance is very important. And in particular for core libraries such as root, it is vital. So root bench system provides an extensible system tracking different performance metrics for the root framework, speculative performance evaluation of proposed changes, and rich and customizable visualizations and aids for performance analysis. Please, next slide. Thanks. The technology that we use in Rootbench is the following, used in Rootbench. Rootbench is based on Google Bench micro benchmarking infrastructure. Micro benchmarks focus on a single function or small piece of functionality. A micro benchmark provides a routine which checks performance only for some concise, targeted functionality. It is useful for monitoring performance of software hotspots. So in the next slide, we can see the information flow of Rootbench. Rootbench uses Grafana for visualization, and InfluxDB is the time series database for Rootbench, given its native support in Grafana. So how does the information flow actually work? The data measurements in the system starts from a set of user-defined benchmarks written using the Google Benchmark framework and compiled to standalone executables. All benchmarks are compiled by a nightly job using the Jenkins framework, and the Jenkins job will compile both the root framework and the root bench software repository against the root build. After each benchmark, the performance data measurements are uploaded into an Influx database. Grafana reads the database and visualizes the obtained data, making it available to the developer community via the Grafana web interfaces. So in the next slide, we can see that the performance analysis of root is we mostly are interested to see wall clock time, user CPU time, memory measurements implemented now only for interpret.
Lilit? Sorry, Lilit, we lost you for 1 minute. CPU
Okay.
time, user
CPU
CPU
time. Oh, sorry. I don't know. Why did it happen? Use CPU time, user CPU time, memory measurements that are implemented only for interpreter benchmarks and for interpreted PyRoot, and stack traces, which is the new feature that I added to Rootbench. So I extended 26 benchmarks in rootbench.git. And some of those benchmarks are actually our data frame benchmarks. Our data frame being a high-level interface for analysis of data stored in T-trees, CSVs, and other data formats. It would be really beneficial to have benchmarks for analyzing its performance. And we mostly use the data reduction methods such as SUM, as it offers the simplest our data frames one of our data frame's simplest operations. So please next slide. Yes. So I extended 14 new R data frame benchmarks in Rootbench. These benchmarks measure different functionality for the data frame using the simplest operation it offers, SUM. For instance, our data frame SUM scalar with for each, our data frame SUM scalar after X defines, etc. And in the next slide, we can actually see already the plots from Grafana. And it is really easy to see that the one that is the slowest is our data frame SUM vector after 5 defines, as it not only does summing of vectors, but also has extra functionality as doing define method 5 times. In the next slide, please. Yes. Also, we extended 12 T-tree reader and T-branch benchmarks in Rootbench. T-branch, they compare performances between T-tree get entry and T-tree player next functions. And we also benchmarked 2 different ways to do summation operation, both for RDF and root T3 player event loop readers. Can we go to the next slide, please? Yes, and the next one. For example, from this visualization, it is clear that T3 SUM scalar T3 get entry is the slowest. The reason for the overhead is the extra functionality that T3 get entry has. And all those performance monitoring plots for the new benchmarks can be also found in Rootbench Grafana. Can we change? Yes. There is a new tool for performance analysis of root. It is the flame graphs. So what are flame graphs? Flame graphs are interactive visualization of profiled software, allowing the most frequent code paths to be identified quickly and accurately. There are different types of flame graphs, such as CPU, memory, off-CPU, hot, cold, differential. It is mostly interesting to see CPU and memory flame graphs for root. The benefits of flame graphs are that all data is in one picture. It is very easy to read and understand the stack traces, and it is interactive when using JavaScript and the browser. In a flame graph, each box represents a function. Stack elements that are frequent can be seen, read, and compared visually. Boxed width is proportional to the total time a function was profiled directly or its children were profiled. Next slide, please. The generation of flame graphs has 3 steps. The first one is to profile the event of interest. So we choose a profiler of our choice. One can use perf, eBPF, system tab, instruments, dtrace, etc. The profile data is a series of stack traces. This profile data is hard to read and can be thousands of lines long, like shown in the picture. It is often difficult to understand how stacks work when looking at this data. The second step is using stackcollapse.pl. This converts already profiled data into a single line of code. The full output consists of many lines, 1 line per stack, and in addition, grep can be used to filter stacks before converting them into a flame graph. And the final third step is when the folded stacks are converted into interactive SVGs. So we get full control of output, very high density details about the event, clear, easy to understand, and interactive visualizations. As I mentioned, there are different type of flame graphs, and now we can talk about CPU flame graphs. CPU flame graphs measure cold paths that consume CPU. In the next slide, please. Yes. Sorry. Here also we can see that this is the stack traces profiled by perf, and it is really difficult to understand which function was which after what. And in the flame graphs, it is very handy and easy for eyes to read and understand. CPU flame graphs measure code paths that consume CPU. They are helpful in understanding that optimizing CPU usage, improving performance and scalability. It is commonly performed by sampling CPU stack traces at a timed interval. In the next slide, we can see that each box in a flame graph represents a stack frame. The y-axis shows stack depth. The top box shows the function that was on CPU. Everything beneath that is ancestry, and the function beneath the function is its parent. The x-axis spans the sample population, and it is very important to note that
Lilit, we lost you for 1 second.
It is sorted alphabetically, and it is not the passage of time from left to right. So code paths split sometimes into different branches, which can reveal key functions. Flame graphs are very helpful when one wants to understand the extra overhead in different events. And in the next slide, we can see an example of flame graph for benchmark T3 sum scalar T3 reader, from which the overhead is obvious, as the main function is T branch get entry. Everything other is the extra overhead of the function. So there is another type of flame graphs that is also interesting in root. It is the memory flame graphs that are very helpful for when analyzing memory growth or leaks by tracing one of the following memory events: allocator functions, BRK syscalls, MMAP syscalls, and page faults. Page faults tracing shows different code paths. Those are populating physical memory. They will be either a memory growth code path or a memory leak code path. And I measure page faults using perf and converted the results into memory flame graphs. And we can see one example of a flame graph on the next slide. This is a memory flame graph. So after having those flame graphs, it is important to have a visualization. So we have 3 approaches to visualize. There are 3 approaches to visualize those flame graphs. One is to generate them locally. To generate the flame graphs locally, one can use the flame graph script in rootbench.git. It has different options for generating the graphs. One can choose to generate them only for CPU, only for memory, or both. The flame graphs will be stored locally in the build directory of rootbench. Another option is to use Grafana SVG panel. The Grafana's flame graphs can be displayed also there. This is a convenient way because rootbench uses Grafana to display other performance monitoring plots as well. And there is a future plan to make it uploaded in a page, so it could be downloaded automatically, generated flame graphs directly from page. I have also done some improvements in the RB support library. I added memory measurements for interpreted pyroot and improved the memory measurements for root interpreter. And in the future items, it would be nice to finish porting of io-tools.git. Those are IO benchmarks from ACT 2017, presented by Jakob Plomer into rootbench.git, and to finalize the PRs about flame graphs and about improved memory measurements in rootbench.git. Thank you for your attention, and again, thanks to my supervisors for the support and throughout my 8 weeks of experience in CERN. Thanks.
Thank you, Lilit. It was such a pleasure to have you as a summer student. Really, it was very nice.
Thank you.
And you did a really great job. It was. I think it's very useful. And there's still PRs are in progress, and I hope like maybe next week I will merge
Yes.
them, so it'll be available in the master.
Thank you.
Any questions? Otherwise, we will move to the next one.
Not a question, but a comment. Thank you for introducing flame graphs. That's a great visualization.
Thanks.
Okay. Thanks, Jim. And next one will be Alfonso Castano. Maybe I need to. And he's working. He's GSOC student for the HSF GSOC CERN GSOC organization, and he's working in root on evaluation of Z standard compression algorithm there. Alfonso, do you hear me?
Yeah, hello everyone. Do I have the chance of sharing the slides so I can move them?
Sorry, tell me again.
Could I share my own screen to show a slide?
You want to share? Okay. I think, yeah, if you want, you can share. Otherwise, I'm already sharing, so you can just tell me the next slide or something like this. How do you feel more comfortable?
I prefer if I can move it. Right now, you can see my slides.
Okay.
Can you, everyone?
Jim, do you see slides?
The slides, yep.
Okay, if that is the case, I will start with the presentation. As Oksana said, I'm a Will Summer of Code student, and I have been working this summer in integrating and analyzing the Z standard compression algorithm in root, together not only with the help of Oksana, but also with Brian Buckelman. They have been great mentors, very experienced people in root, and thanks to their advices, we have made a lot of interesting progress. So, as probably all of you know, at CERN, the amount of data that is generated by experiment is pretty huge. Because of that, compression is absolutely fundamental. However, it's well known that compression comes with a cost. The more compression you get, the longer time it takes. Because of that, nowadays, root supports basically 3 compression algorithms. SMA, that offers the highest compression ratio with the lowest speed, CLIP, that offers a balance between compression ratio and speed, and LC4, that offers higher speed at the cost of lower compression ratio. My work has been focused on Z standard, which is a new algorithm that also aims to offer a great balance between compression speed and compression ratio. Basically, what in theory promises is to achieve better compression speed and better compression ratio than linear metrics, and in some scenarios to be pretty close to some of these more specialized compression algorithms. Before showing the results, I would like to give you a quick idea about how compression works in Z standard. And for that, I think that the good way of starting is to talk about CLIP, because CLIP, which is an older algorithm, still keeps the fundamental of this new of Z standard. Basically, in CLIP, we find 2 main elements, LZ77 encoding and human encoding. LZ77, what it does is something quite intuitive, that is to try to find occurrences of a string previously in the file. So if you are finding a very long string of text or bytes or whatever, if you have already seen this exact same text, you can say, hey, instead of repeating it again, you say, I saw this n bytes ago. So you save space that way. Human encoding, on the other hand, what it does is to analyze what words appear more often and give short code words for those words that appear more often. So even if you have a file that you're repeating the same phrase very often, you can just encode that phrase with 1 byte, with 1 bit, and say, okay, 1 bit represents this phrase because it's very, very common. So based on that, ZSTD includes several improvements that I want to highlight a few of them. One of the most interesting ones is arithmetic encoding that is introduced in the form of finite state entropy that in ZSTD is combined with human encoding. So what it does is that arithmetic encoding solves one of the main problems of human encoding. That is that the minimum length that a word can have is obviously 1 bit in human encoding, but arithmetic encoding, through kind of a complicated math, is able to assign, let's say, fractional lengths of words. For example, 0.1 bit will encode the most frequent word. This has almost never been used before due to the long time that it takes to do arithmetic encoding, but finite state entropy is a very recent implementation that has been able to overtake this limitation. And on the other hand, another very interesting feature of ZSTD is the advanced control that it gives you of dictionaries. Compression dictionaries in ZSTD, they can be reused, they can be saved, they can be generated from samples of data. For example, you can give a lot of different samples of data and say, hey, can you give me a dictionary that is in average good for all of them? And this has been very successful in different projects like Facebook, for example. And apart from that, just to mention that ZSTD is newer, it has made many design decisions that are more suitable for recent computers, like to be more optimized for parallel computing or branches that come with a high cost. So about the results, what we have seen in different benchmarks, in different files that are very often used at CERN, is that in all cases, it's offering a better results than CLIP in all the aspects as in theory it was promised. And it stands as the best algorithm in compression, in the balance between compression ratio and compression speed. Here I'm showing a file from CMS, nano IOD file, which, although it's a small example, it shows the pattern that we see in other files. Like here I'm showing results from LHCb, that is also very common. And again, even if the file structure is totally different, we still see how ZSTD outperforms the CLIP in all the aspects, and again stands as the best algorithm in the balance between compression ratio and compression speed. And in a more synthetic example that is not particular of a certain experiment, but a synthetic one, what we see here is, again, even if it's not a typical certain experiment, ZSTD again stands as the best option in this balance. And the compression speed that we have seen here is that ZSTD is very close to LC4, that is the fastest alternative, while taking a big advantage over CLIP. And the good part about all of this is that thanks to the work that we have been doing, all this is already ready to be integrated inside the root. We have been working with the community, getting feedback, polishing the code so it can be nowadays easily integrated without any further change unless it's requested. And from the day one to start providing benefits to the users, to give higher compression speed, higher compression ratio. And this is not all what we have been doing. Apart from this, that is a work that already Brian and Oksana have been working on very heavily. I have been also working in how to bring more advanced ways of compressing with ZSTD in root. One of the problems that, from my point of view, root has is that all the compression is done separately. So you compress every chunk of data through a different request. So you cannot try to take advantage of having a centralized unit that takes care of all the work. For that purpose, I have been working on an idea that is a compression engine, that is a single class that processes all compression requests, and this way they can share common resources, don't need to be initialized multiple times, and also control the way dictionaries are being used thanks to the new option that ZSTD is offering. So to understand this, I would like to give a bit background about how root files are structured. Basically, in root, we usually find what are called trees and tuples. And inside each tree, as you can guess, we find branches. And branches usually are storing values that correspond to the same variable. And finally, inside a branch, we find baskets. And these baskets are finally memory buffers that they store the information. They are not necessarily contiguous in memory, and this implies that they are compressed separately. So instead of compressing the branch as a whole, like we could be seeing in this image, and this green part would represent the dictionary, we are compressing separately each basket. What does it mean? That instead of having one dictionary, we have several dictionaries, which introduces a significant overhead. And we cannot easily solve this problem because, as I said, these are different buffers, they are compressed separately, and right now, without a centralized unit, this would be impossible. So at this point, what we were trying to achieve is how to find the way of using the same dictionary for the baskets within a branch. So for that purpose, from all the features that ZSTD offers, we decided that the best alternative, due to the nature of root data, is to try to use the same dictionary for all the baskets, and this dictionary will be the dictionary of the first basket of the branch. What does it mean? This means that if the first basket is of the same, it represents the same data and is representative of the rest of baskets, then we will keep a good compression ratio and at the same time reduce the overhead of having to store so many dictionaries. At the same time, we could potentially improve the compression speed since the dictionary would only be generated once. And the only drawback that, well, this is obvious, is that the compression ratio could drop if the first basket is not representative. However, as you remember, I have said before that in root, branches usually store information from the same variable. So I have been implementing an initial approach for this, and what we have seen is that nowadays, only in a few cases, we have been able to obtain an improvement in the compression size, in particular in a nano AOD case. In almost, unless in a very particular example of LHCb that has turned out to be a very complex file in the sense of its underlying structure, what we have seen is that in some cases we have found potential of this approach of reducing the first basket, and in others not. There is a very deep analysis that me, Oksana, and Brian have been doing that I don't have the luck of presenting today because it's very long. But what we have seen is that every single file has a different structure. The way baskets are organized is very diverse, and these difficulties, the fact of being reduced in the dictionary for such different baskets. And about the speeds, what we have seen is that compression speed, unlike we were expecting at the beginning, is suffering. We are seeing a regression, by some cases that is 50%. And this is something that we are currently investigating on, because although some of these hypotheses, I even was in touch with the author of ZSTD algorithm to know what is the potential that we may see. The fact is that we are not achieving any benefit but a regression in compression speed, and the analysis that we are making is probably suggesting that this is due to the lack of uniformity in the size of baskets, because we are seeing that there are some very small baskets, and this makes harder to use a dictionary that is good for a very big basket, but is not so good for a smaller one. And in the compression speed, we are not seeing that much different. We see in some cases a small regression, but nothing significant. And the fact is that here, due to the nature of set standard and other compression algorithms, the difference that we may expect is limited, because these algorithms are very stable no matter the compression level. So here we could still try to find ways of achieving an improvement, but the room for improving or regression is quite limited. So what have we achieved so far? Basically, nowadays we have set a standard in its baseline way, in the fundamental way, that we have shown that it outperforms in all metrics through the whole algorithm, CDIP, and it stands as the best algorithm in the balance between compression ratio and compression speed. On the other hand, thanks to the work that we have been doing, it's already completely adapted to root. Is also tested, and it can be merged here with one click. And also another advantage that may not seem so obvious is that set standard is a new algorithm. There is a group of very talented people working on it, more or less supported by Facebook, and still month after month we are seeing that they are making improvements. They are making improvements that produce benefits almost for, let's say, for free, and this tells us that we can expect to see even further improvements in the future. And on the other hand, this will unlock the use of this very rich API that set standard offers, that although we haven't been able yet to find a way of outperforming the fundamental way how set standard works, this will let us approach compression in a more transversal way in root.io, and at the same time this also has motivated a deeper research in the way files are structured in root, the way baskets are distributed. As I said, I have been able to make a deeper analysis that I'm pretty sure that will be not only helpful for set standard itself, but for any compression algorithm and for root.io itself. Basically, this is all what I wanted to share today. Thank you very much for your attention, and if you have any question.
Any questions from outside? Okay, it was pretty clear slides, even though, of course, it is not the final result, and there is still opportunity that in next week or maybe two, until the end of the program, there will be some new results. And then the plan is to test recent NOD to have some like better results in this case, because the file that was used was a bit old, and also so it's from 2017, and this will be not anymore the same even version of NanoAD in this case. So yeah, Alfonso is doing an amazing job, and I'm really happy to work with you. It's a super pleasure.
Thank you, Oksana.
Hi, this is David. Do you hear me now?
Yes, we hear you.
Okay, I was talking to myself before. I had a question, maybe especially if you're going to try to update results. The sort of trade-off graphs on slide 6 or 7, for example, I think at least for CMS, we're more interested in decompression speed than we are compression speed.
Yes.
That's what our users, that's of course what our users experience. So it'd be great to see that trade-off as well.
Alfonso had the preliminary results, but for decompression, but we realized also after feedback of from root team that probably the way how we are measuring decompression, it is not correct. So we prefer maybe to show it once more in different iteration than to show very the results.
Yeah. Basically nowadays the data that we have just generated is not totally isolating the compression part, so we may be introducing a little of overhead that, although is common for all algorithms, we cannot make a fair one-to-one comparison. And today I wanted just to show all the results that they are totally verified, but definitely we are working to have very soon the compression results isolated and reliable.
More questions?
Well, so I was wondering, you said toward the end that Facebook is continuing to make improvements on this. If there are improvements in the compression algorithm coming from the pipeline, are those in such a way that if you were to add this to root now, it would be backward compatible or would not be? Because I can imagine two different kinds of improvements to the algorithm.
You mean that what we're using now with the dictionaries, and if, for example, there will be a new development and, I don't know, schema will be changed and everything, yeah, it probably introduced a risk that that it will be hard to provide. But I'm sure that in this case, Facebook is actually aware of this problem, so they provide kind of so the schema is the same and the header is the same, so we should be able to do this.
Yeah, obviously there's always a risk, but it's also true that ZSTD has already deprecated quite a lot of stuff because it's quite mature, even if it's new. And I'm not sure that they would deprecate such a fundamental aspect, and especially if something will be ever affected will be the dictionary stuff, the baseline compression. I think that it will never be affected.
Yeah, because I was asking what kinds of changes these are, because if they're changes that work within the existing framework to just make better compressed files versus changing the framework. That was what I was asking.
No, in this case, from the point of view of like framework, I think it's pretty stable product, which is it's not like beta version or something like this.
Yeah.
It's 1.8.5, so they really have a lot of releases, and it's shipped also as a part of the. So you can easily install with your package manager. You don't need to build it by hand or something. So I feel like it's pretty mature product in this case. The other thing that, of course, there is a lot of improvement and a lot of, so if you can see their releases, they basically, because of community and because that it is widely used by other companies, etc. So there is a lot of nice improvements, a lot of nice new functionality, and its other point is that it's also important to trace it and check it out. How can we improve in this case? But it's still in our case, it's still there is only there is OpenPI, so it's not even in the root. It's all the results that we are showing is basically the evaluation of made from Alfonso branch.
Okay.
Yeah. Okay, so next one is David and Jim. I think. Do you see slides? Charles, do you want to share them?
Hi. I can share my screen. I believe. Get that going.
I don't see it, so.
Yeah, not yet. For him though.
Yeah.
Share your screen.
There it is. Okay.
Okay, and it's
Okay,
still,
great. Now I see. Yep.
Is that working now?
it's good.
Yep.
Okay.
Jim, David, do you want to present Charlie?
Well, I can give you an introduction. So Charles was our Google Summer of Code student, working on a precompiled version of Awkward Array, and we liked what we saw enough that we're basing a future version on it. Other than that, I think I can let Charlie describe it.
Yeah, so hello everyone. My name is Charles Escott. I am a computer science and electrical engineering student currently going to Sacred Heart University. Yeah, so as Jim said, I worked on a precompiled version of Awkward Array. Yeah, I guess I'll get into it. This was kind of a dream project for me because it was very C++ and data structure oriented, which is very fun. So the issue that I started to solve is that, well, to begin, why do we have Awkward Array? We have Awkward Array because particle physics data is often too complicated for normal data structure types. For example, normal rectangular arrays are, well, you have to have a set length for every dimension. And in many cases, that is not the case with our actual data. And as a result, we need to create special types of arrays with different functions that work better for the particle physics data. For example, jagged arrays, as are seen here, this is a very small jagged array, have varying length for one dimension. So you can have different indices that have lengths that are not equal. Right now we have Awkward Array that is coded in Python and Numba, which is a little faster than normal Python. I guess we're working on that. But the problem with that is that Python is just-in-time compiled, which means that it has to, it does a lot on runtime rather than compiling it before and just working with the machine code. And that causes it to be slow to run. So the solution to that is implementing them in a precompiled version. In this case, we used PyBind 11. And what PyBind 11 is it's a library that allows C++ code to be exposed to Python so that it gets compiled to Python bytecode. So this would allow me to create a library that's written in C++, but you'd be able to use it in Python as if it's a normal Python library, which is very nice. So these are examples of different awkward arrays, and the one that I worked on the most was jagged arrays, which is apparently used by far the most of all of these. It's also got a lot more code in it than most of the other ones, so I just focus on this for my summer project. To begin with PyBind 11, PyBind is a very nice library in many regards. I found it to be very hit or miss. For example, it has a lot of useful tools in the binding code. This is an example of a binding on the right. As you can see, it gives a format to write a class that connects a C++ class to a Python class. I can attach the normal C++ constructor to be run as the init method in Python, and then I can attach class and object methods to that with my own custom names, and it will just attach whatever compiled code from the C++ to that to that name is when it's called. The only thing that I found was impossible with Python 11 was having C++ inherit from Python classes, which was a little bit of a bummer because when we started this, I was working with a version of jagged array that was a subclass of the normal Python jagged array by using the multiple inheritance with Python. Instead, I have a Python class that was inheriting from both the C++ and the Python. And so anything that I didn't fill in with the C++ would be finished with the Python. Although at the point that the project is now, I've got that completely separated from the Python, so now it's fully C++. Things that go between Python and C++. I found that I was able to implement methods like an item, string, length, etc. Just naming them certain things like one would in the Python, and it worked seamlessly. And then I was also able to access those in the C++, along with many of the Python types that are listed here: object lists, tuples, arrays, etc. There are lots of other ones, exceptions and strings. All were automatically translated. So most of the questions that would come up about, oh, you know, how viable would it be to create code in C++ to work with Python? It's pretty intuitive in that most of the time it was just, okay, I'm coding in C++. As long as I get my binding code right, which wasn't that hard, it carries over pretty easily to Python. The memory ownership was a big question, and I found that well, like everything else, it wasn't that unintuitive in that because Python uses reference counting, which means that any variable that has at least one reference to it will not be collected or I guess deallocated. But this now carries over to the C++, so I found that anything that's exposed to the Python or not, as long as I keep at least one reference, it would not get overridden, and I ran lots of tests to figure out whether or not that would work. There was only one time that the memory ownership became a problem, and that was, well, I can get into that later with the next slide. Unique pointers and shared pointers from C and or C++ are supported, but usually it's best to just let the Python 11 and Python code do the heavy lifting instead. Okay, so NumPy arrays are, as you can see in the buffer info struct, often, so all these elements are aspects of a normal NumPy array, in that you have pointer, item size, etc., that define what an array is, along with the shape, which is different lengths for different dimensions, and the strides, which is how the step works through the contiguous data to define what an array is. In Python 11, arrays are implemented in a normal array class, which is not typed, and an array underscore t class, which is templated to whatever type you put in. The benefit to this was that I was able to work with the arrays without having to worry about type in many cases, because the pointer is a null pointer, or it's a void pointer, which means that I can just attach a type to it and it'll step through based on that type. The con to this is that there's lots of code involved in making this implemented. For example, Yeah, so here's an example of one of my methods for traversing through an array that has at least one, if not more dimensions. And because the arrays are implemented like flat arrays, to step through them, you have to go through into the strides, and the first little green circle, I guess, yeah, the get item part shows how get item works with array. Don't pay attention to the fact that it's a C array struct. I'll get into that in the next slide. But I had to kind of create a bunch of extra lines for each line that would normally be much easier in Python. So in Python, normally, to get an item, you just do the array name and you make a bracket and you put the index in the bracket. Here, you have to get the pointer, you have to get the index, and you have to type it, which seems like a lot more work. But in the end, having it compiled beforehand makes it much nicer and much faster. So the C ends up being very useful. After I got everything situated and I was working on the jagged array in C++, getting over the initial hurdles of not knowing how to do things, we decided to go into a different project architecture. There were lots of different sections of awkward array. There was the normal Python awkward array, then there was awkward numba, which is awkward array being implemented in numba, which I believe is another type of Python, but it's compiled differently. And then I was working on AwkwardCpp. And then to simplify everything, we changed direction towards this project structure, which says it's really just
You cut out. Does anybody hear us?
Yeah. Let's wait a few seconds, maybe.
Yep.
can hear.
Yeah.
We can hear now. Good.
Okay, yeah. I guess it just muted for some reason. Okay, where'd I cut out? Okay, well, there's this new project architecture. It's got C++ and numba sides, and they both draw from CPU functions and GPU functions, which, when implemented, will make everything faster because they're both drawing from precompiled, or I guess the C++ is compiling everything beforehand, and having the GPU later would make it go much faster to be run on different hardware. There were some issues switching over to C. Because first I was saying, okay, well, we've got C++ and we're going over to Python, but now we've got to do C to C++ to Python. And I haven't really done a whole lot of C in the past. But it turns out that except for these bullet points which I listed, which are that, there's no template support, you can overload functions, no classes, exceptions, or booleans. On the C side, it was very similar, so I was able to go through my C++ code, find all my for and while loops that seem kind of computation heavy, and then re-implement those in a separate C file, which I would then call from the C++, so that later when the numba section is implemented, it can also use those same methods in the C file to be used in numba, because numba can't use C++, but it can access C. Additionally, all the C methods were clean of memory management, so everything that went into the methods was simply a pointer to something else, and all the return types were, well, there was no return type. It would just alter the variables that were sent in, which can be shown in this one. At the very end of the signature, it shows int32 pointer to max, that was just the output, and it was a pointer to that. So it would not leave any of the data handling to C, or the management. That was pretty nice. So in the end, I put together a library that will now be a solid basis for Awkward 1.0, which is the new project architecture that was shown in this slide. And there was a lot of troubleshooting involved in this, and I made a lot of code, and as a result, I have a lot more experience and information. And because the documentation for PyBind 11 is, great at some times and completely non-existent at other times, I'll be able to help with the writing of the C++ for the rest of the project for Awkward 1.0, which is now going to be implemented in C++ and Numba. Additionally, I have this jagged array class which is what I actually did, and that's probably going to be moved a little bit around now that we're moving over to a different project architecture. But what I have currently works like a normal jagged array class. I completely disconnected it from the Python, so it stands alone as a C++ precompiled class, and if I run it in Python, you wouldn't be able to tell whether or not it was a Python class or something in PyBind 11. And that's it. Is there any questions?
Yeah, I have a tiny question. So what will change for the users actually? Because I mean, Awkward Array, it was before 1.0. It was already ready product. What will be changed in API or something like this? API.
So I think the reason why we're switching towards the Numba and C++ models is that it will, most importantly, make everything quite a bit faster in most cases. Additionally, Jim mentioned that there were some complaints about method naming for the way that so if people wanted to make their own code for the projects so that they could make a custom method, the way that the methods were named, it would kind of get a little messy on what was overriding what, because there was I think the cross method was having some trouble, and that will also be cleaned up in the Awkward 1.0 project.
Yeah, I could describe a little bit more, because this is a question about beyond your work here. So first of all, thanks for a great presentation.
Thank you.
Actually, the main emphasis for this architecture change is not actually speed, although we expect to get some improvement from having single pass rather than multi-pass. But the main intention is for flexibility. The fact that you can write for loops in C++ without consequence. And for that kind of refactoring, it doesn't need to change the user interface. However, actually in this project that we're starting, we do plan to change the user interface because there were some things that users are using it and they are giving feedback about what's confusing, and some of these things need to change. And so at a major release boundary is a good time to make those backward incompatible changes. So the example with cross that Charlie was alluding to is the fact that we're putting all these structure manipulating functions as methods on the object, but a use case for this, physicists are putting their own methods on the object, like domain-specific physics methods. Cross is a good example of this, because we were using cross to mean like an SQL like cross join, but for 3 vectors, it had a physics overload for 3D cross product. That was the first example of a name collision, but name collisions like that can be common. So among the interface breaking changes that we're planning would be to separate those namespaces so that they cannot collide.
Thanks.
Yeah.
Other questions?
I can bring it back down.
Okay.
Well, thank you everyone for listening to my presentation.
Thanks. It was great.
And thanks, Jim and David, for being great mentors. This was a really fun experience, and I learned quite a lot.
Thank you. Same here.
Yeah, thanks especially to Jim, who I think did all the mentoring. Very good. I think we're done today, unless there's other comments. Hopefully we'll see people again on Wednesday for 3 more talks. So thanks everyone for coming.